Okay. Um, so regarding the final projects, I will have feedback to you guys on your proposals either tonight or tomorrow morning. So they'll be coming shortly. Make sure to incorporate the feedback that I provide for the proposals. You have, I guess, this week and next week. And then in the final week of class, we'll be doing the presentation. So remember, I am not going to be able to be present, but our TA, Grant, will be here. The way we're going to do it, we'll have a random assignment order for the project presentations on Tuesday and Thursday. It'll take 2 days to get through all of them. So you guys will present to your peers, and then it'll be recorded so that I'll be able to view them while I'm gone. Okay? Any questions about the project so far? No? Okay, and then the last thing, just remember that the presentations, and I'll remind everyone again, but the presentations are due at the start of class so that everyone has the same amount of time. And then the final report following everything will be due on the last day of finals. Okay? Okay, so let's see. So we are going to do a lecture. Oh, let me zoom out and come over here. Okay, so we are on lecture 15. Okay, and so we are going to start off by talking about or kind of foraying into some machine learning methods. So we're going to start off today specifically looking at one of the approaches that's used for classification. And normally we've been looking at these kind of discrete variables where we have different classes. This one's going to be a little bit different. We're going to try and think about the sort of visualization of data to kind of understand what's going on here. So we're going to start off by talking about the hyperplane. So this is a flat affine subspace of dimension p minus 1 in p dimensional shape or space. Don't get too hung up on this here. This is basically a line in 2D space or a plane in 3D space, and then whatever you call it in n dimensions, right? But it's something that can essentially bisect the space that you're working in whatever dimensions that you're in. So an example of this would be something like if I have x1 and x2, and I've got a bunch of points like this. Right, I can divide, I can divide the space into these two territories using a hyperplane. So if you recall, back to the logistic regression, and we also looked at the k nearest neighbors, right? It's able to divide the space into boundaries. You might imagine that the red dots may indicate if this was a binary outcome of yeses and nos, the reds might be yeses, the blues might be nos, and I can draw this hyperplane to divide the spaces where I would be able to then predict that all the stuff in this space would be yeses, and all the stuff in this space would be no's. Okay? So in 2 dimensions, you end up looking something like this. In 2 dimensions. And then generically, in p dimensions, we end up looking like this. Beta 1 x1 plus beta 2 x2 plus dot dot dot. Beta p xp equals 0. Okay? So the logistic regression is a specific technique to draw this kind of hyperplane. And we're going to think more generically about how you can draw this hyperplane through sets of points. So we're going to build from kind of the simplest example to a technique that is more commonly used today in some machine learning approaches. Any questions about this so far? Okay, so the first one is the maximal margin classifier, also known as an optimal separating hyperplane. So this is a separating hyperplane that is farthest from training observations. Okay, so let's do another quick example here. I'm going to do my x1, my x2, just draw a couple of points out here, and then I'll draw a couple of points over here. Okay, so the whole idea is I want to draw a hyperplane that will separate these guys. So how many hyperplanes can I draw? Is this a valid hyperplane? Yeah. How about this? How about this? And so on and so forth, right? I can infinitesimally change the angle a little bit and still maintain a valid separator between our two groups. So technically speaking, there is an infinite number of separating hyperplanes. So this is the first problem that we have to deal with, okay? So how do we do this? x1, x2, let me draw so so the math of this looks something like this. I want to maximize with respect to beta 0, beta 1, and so on. I'm going to write the sort of generic version, comma m. So maximize m such that j equals 1, p beta j squared equals 1, where yi of beta 0 plus beta 1 xi1 plus beta 2 xi2 is greater than or equal to m for all I equals 1 through n. So the idea here is that there's a particular hyperplane that we want to draw. And that is known, so let me draw that. I want to draw a line through here such that if I look at the perpendicular distance from the closest points to the line, so that would be something like this, maybe something like this. The idea is you want to maximize distance of closest points to the line. So if I perturb this line just a little bit, the idea is that the distance to the closest set of points to the line is actually going to increase, right? And so no matter what direction that I wiggle this line or move the line, you will actually get closer to some of the points. And the line is built up of these distances, which are known as support vectors. I kind of think of them as like pillars that are holding this line in place, right? So if you imagine there's like a physical pillar to the line, if you move the line in any way, the pillars should be in totality getting larger, they will be getting, in theory, smaller. And so this hypothetically would be the line that gives you the largest size pillars, essentially. Okay? Any questions about this? Okay. So, this is a kind of a first step, right? This is a necessary technique for us to work out how I draw one separator given a sort of infinite set of possibilities, right? So we've reduced this stuff down to essentially one line. Okay, so that's good. What are some problems with the maximal margin classifier? We're going to say this is going to be called MMC. What do you guys think? Can we do this for all types of problems? What's the like really obvious one? Huh? So look at the data. So the reds and blues. Okay, so let's make this a lot more abundantly obvious. Okay. Who can draw me a line that will separate these into our two categories. Anyone want to volunteer? No, okay. Not possible, right? So this is known as non-separable cases. And this is very common, right? You can, like, think back to our Disney example where we had the movie ratings, movie length, and then the popular ratings, right? They're interspersed all over the place. It wouldn't have been possible for us to create these like well separated categories. So that's one problem. The other problem is a little bit more subtle. And I'm going to see if I can draw this accurately. So we have x1, x2. This stuff doesn't matter. And then we'll do something like here and here. Okay, these ones don't matter. Okay, and let me actually copy this. Uh-oh. Did we freeze? Okay, one sec. We'll close this. Whoa. Oh my gosh. Here we go. Sorry, that's just me being lazy. Okay, so the other problem, the second problem, is, so let's draw our separator here. It might look something like this. Is if I were to add a point, then the line is very sensitive to individual observations, right? Especially if they're at the boundary. So our second problem is sensitivity to individual observations. Okay? So we are going to talk about a more complicated approach, or kind of the next step, next evolution here, which is known as a support vector classifier. So it's building off of the maximal margin classifier, but it addresses essentially those two issues. So general robustness to individual observations, and then better classification of most training observations. So the idea is we do the same optimization as MMC, right? So that is this thing over here. We're going to do the same optimization, except this time we're going to add an additional constraint. So this will be 0 is less than epsilon I is less than 1. And we're going to have the sum of I equals 1 to n of epsilon I is less than or equal to C. Okay, I'm going to talk about what these are in just a second. For the optimization of M, we're doing quite literally the same thing. So like this, so on and so forth. Except on this side, we have 1 minus epsilon I. So this is a slack variable. Okay, so in English, what actually changed? What are we doing here? Epsilon tells us essentially how many points can violate the margin. And so this here would be inside the margin, and then if epsilon I is greater than or equal to 1, this would be outside the margin. So this would be misclassified. And C is our budget for number of epsilons that violate the margin. Okay? So now you're allowed in your optimization to be in the wrong place, right? So now you can have a red dot in the blue area, and that's totally fine. And whenever that happens, your epsilon will be larger than 1. It's like on the wrong side of the curve. And you can allocate a budget for how many times this can happen based off of C. And so C is really our tuning parameter. So if C is really, really large, then I can arbitrarily put the line anywhere I want, right? Because then the number of violations that you have is, you're allowed to have any amount of violations. And if it's really small, right, then you're essentially having a small budget for violations or not allowing any violations at all. How do we choose the value of C? Cross-validation, yes, thank you. We're back to that. Right. And at C equals 0, this is the exact same thing as a maximum marginal classifier. Okay? Any questions? And we're gonna do examples of these in R kind of all together. So that is number 2. The last one, so the last evolution of this, actually, I should say, with this now we're allowed to, for example, here with an SVC, I could still draw a line here, right? And that I have a violation, so this would be an SVC fit. This would be an allowable violation. And I might prefer this original line just based off of minimizing the sizes of those pillars, right? Or sorry, maximizing the size of those pillars, the support vectors. It's the support vector changes in definition a little bit in the SVC because you're allowing for these penalties, but in general, it's going to be, similar to essentially what we described. There's one more drawback here before we arrive to kind of our final model that most people like to use. And what is that? What might we like to be able to do when we're separating these points? What do you guys think? What about if I did something like this? How would you like the hyperplane to be oriented here? Yeah.
In a nonlinear kind of circle-ish way.
Yeah, right. So the problem, right, is that, okay, I can now have a budget violation. So maybe if I drew a straight line, I could do something like this, right? But like these classes are very clearly separable. And so ideally I could do something like this. Okay. And that's what we do in the final step. So 3 is a support vector machine. This is also known as an SVM. So this is a classifier that basically allows for nonlinear separators. And the way that it does this is, so it modifies and generalizes computation of the SVC using local regression. So SVC uses a linear kernel, whereas SVMs can employ more complex kernels. So polynomial, radial, and so on. And so when you formulate the hyperplane, it no longer has to be constrained in a linear way. So one sort of little thing to pay attention to is that most machine learning libraries use a different formulation than the one that we've been talking about. So instead of maximizing the margin, it will instead minimize. Yeah, so we don't really need to get into the guts of this here, but just to show you guys. So the margin, which we were calling M before, is equal to 1 over W. So maximizing this is equal to minimizing this, which is where we see kind of the difference in minimizing versus maximizing. The other thing you'll note here is that the slack is a little bit different. So most packages will do C is a penalty rather than a budget. Okay, so in a lot of textbooks, they do the opposite. So just be aware that when you're putting in values for C, you're increasing the penalty as opposed to increasing the budget. So that what effectively that means, large C equals slack is more penalized, and model avoids violations, right? As opposed to in the SVC, the C is a budget, and the larger the C is, the more violations you're allowed to have. Small c equals slack is less penalized. Model allows more violations. Okay. Yeah, I'm not sure why they ended up using the same variable to describe these, and they didn't change it, but this will work the opposite way you might intend if you are using more textbook definitions of the tuning parameter. Okay. All right, any questions? Okay, so then let's jump over to R. I do have a data set that's uploaded into Canvas already, so we'll use that for the support vector machine example when I get there. So just note that you might need to download that. We're going to use E1071 library. This is the library that has a lot of the functions to do SVMs and SVCs. And then we'll use ISLR and ggplot for graphing. Okay, so let's start off with a support vector classifier example. And then to make sure we all end up with the same one, I'm going to set a seed. And we're going to do some draws. Like so. Okay. Oh, I have a little mistake here. This should be like that. Yeah. Oh, no. What am I doing? Rep. Oh, I need a C here. All right. So if I plot this, we should look something like this. Okay. So we'll have points designated into our two classes, blues and reds, negative ones and ones, basically. So we have binary outcome, and let's organize this into a data table. And we're going to do a linear fit. So SVM, support vector machine, we're going to regress y on our x's. And then that's going to be coming from dat. Now, if you want the hyperplane to be a straight line, we're going to use a linear kernel. And I'm going to set a budget of, not a budget, a penalty of 10. Okay, so this is, the cost is our tuning parameter, which is a penalty, right? So the larger this is, in general, the more we're going to try and avoid the violations. Every violation, the cost of the violation is multiplied by 10, essentially. All right, so I can run this. We can do a summary. And what this will tell me is we have a classification. It uses a linear kernel. My setting, my cost penalty setting was 10. Out of the points here, it's saying that 6 of them are acting as support vectors. So we have essentially 6 pillars, right, connected to our hyperplane. And there's 2 classes. So let's see what the plot of this looks like. All right. Okay, so don't worry about the shaded region for a second. We are going to focus on the points. And there's 2 dimensions to look at with the points. So one, we have circles and X's, and then we have color of the points, black and red. Okay. So the X's indicate that the point is acting as a support vector. So you'll see the points closest to the separating line are X's. So we should have 6 of them. 1, 2, 3, 4, 5. Yeah. So actually, I'm pointing at them. You can't see what I'm pointing at, but 1 over here, 2, 3, 4, 5, 6. Okay. The color of the point indicates the true classification of that point. Okay, and so we had them as blue and red before. Now they're black and reddish pink. So when you separate these across territory, we actually see some of them are being violated, right? So if you are a red point inside of the yellow region, or if you're a black point inside of the red region, that means that you've violated the margin, but that's allowable in support vector classifiers, right? Because we have that penalty term, the epsilons that allow the violations to happen. So how many violations are there in this graph? Two. Yes, that's right. We have one red point in the black point territory, and we have one black point in the red point territory. Okay? Yeah, and so this is a way for us to give predictions, right? We are firmly away from inference territory in the prediction territory. So if you need a model that's just telling you what class you should belong to, SVM is going to be a pretty powerful tool to do that. Okay? Any questions about this? So that was our support vector classifier. We're going to now look at our support vector machine using a radial kernel example. So now we're going to load in the file that I was mentioning earlier. It's called eslmixture.rda. We'll load that in. Here we have a bunch of different columns, x's, y's, predicted, probabilities associated with each one, the marginal classifier curve. We only need a few of these. So what I'm going to do is plot x. Okay. So here is our new data. And what you can see is that it's a lot more sort of mixed together, right? And so we want to be able to draw some kind of hyperplane through this with some allowance of violations that will give us the best hyperplane that will maximize, right, the support vector distances, but also at the same time try and keep our violations to a certain level. So this is why these models are very powerful. They are very flexible in being able to deal with violations and nonlinearity. So we're going to do basically the same thing as before. Except this time I'm going to do a radial kernel. So factor y, regressed on everything. Oops, kernel equals radial, and we'll set the cost at 5. So it'll be a smaller penalty term that will allow for more violations. We'll do summary. Oop, have not run it yet. So here, same thing. Now it tells me it's a radial kernel with a cost of 5. I have 103 support vectors, so quite a lot more this time, but still 2 classes. And let's take a look. At this. Oop. Oh, what happened? plots. Oh, here we go. All right. So this time, I draw a plot that looks like this. So highly nonlinear, just by using a different kernel. This leverages the similar to some of the kernels that we talked about in our local regression example, and thereby allowing us to have this highly nonlinear fit. You can see there definitely are a large number of violations, right? We can see there's, all these red points in the black area. And then you have a bunch of black points in the red area as well. Okay. I should mention again, the X's are our support class or our support vectors. If you are in violation, you're actually automatically a support vector, and so you have there should be no red circles in here, and there should be no black circles here. You should be a support vector, aka an X, if you are in violation. Otherwise, we should see most of the X's in the area surrounding the borders. Okay, there are some X's out here in red, and that has to do with how the definition of the support vector changes in the SVC and the SVM. But for the most part, our X's are going to be kind of propping up this boundary line. Okay? Any questions about this? Yeah.
Last week we looked at like grouping and there's like multiple groups. Why are we only looking at two in this case?
You're talking about like the clusters? Yeah. So that's the clusters is a very different approach. So clusters, remember, are unsupervised learning, so there's no Ys. Here we have outcomes. The outcomes being, ones or zeros. You might imagine this being the analogy to our previous example, it would be something like x2 was our movie runtime, x1 is the popular vote rating, and then the color of the circle would be if it's PG or PG-13, right? So you're trying to determine a boundary that would separate them, and the Y's in this case have two classes. It's red and black essentially, but you could have more classes, and your separator would get more complicated. Yeah. In this particular example, we're just looking at a breakdown with two classes. Yeah. Any other questions? Yeah, so this is a prediction-based model that folks in machine learning specifically for classification. And so if you're doing some kind of analysis where you have these discrete outcomes, and you primarily just care about building a model that can predict those outcomes, SVM is a very powerful, flexible tool to do that, right? But unlike something like the logistic model, where we are able to say something about how the boundary is derived as it relates to variables in the regression. Here, there's no ability for us to say anything about how this boundary relates to the variables themselves. So your ability to do interpretation of particular variables, you can't do that in this model. Okay? All right. Any questions before we move on? All right, so we're now going to talk about a different topic. So this will be new this year. Got a couple of requests from students to talk about this in the past. So I'm gonna put something together for us to cover this. We're kind of in the right section. We're branching out of all the like causal stuff, and then some of the side stuff with the unsupervised learning. We're starting to delve towards more complex machine learning approaches, and this is a nice kind of go-between before we get to like neural networks. So we're going to talk about decision trees. So this is a supervised machine learning algorithm that works like an interactive flowchart. To make decisions by breaking down data sets into smaller subsets by asking hierarchical if then else questions. So let's suppose I wanted to predict EV purchase behavior. I could first divide my data. So income, let's say, is greater than $75,000. If yes, then we'll do something. If no, maybe this will predict no EV. Okay. If yes, maybe we'll ask, does this person own a home? If yes, then maybe you... Oh. Yes, maybe here we would predict yes, EV. And here, if they say no, maybe we predict no EV. Okay. So this is known as a decision tree. Here we have what's known, here I'll use a different color. Here, this is known as a root node. This would be an internal node. And then these guys would be known as our terminal nodes, also known as our leaves. So I guess it's like an upside down tree. So you can imagine you have data, you have a bunch of y, you have a y and then a bunch of x's. And essentially on the y end, you want to divide the y's out such that they're separable based on variation in my x's. And so in this particular case, one of my x's is income, and I decided to divide it at the 75K breakpoint. So you can divide based on continuous variables, such as income, and then in the next internal node, we divided it by whether or not you owned a home, and that's sort of naturally divisible, okay? And the idea is you want these categories to be essentially as pure as possible, right? You want the resulting groups to represent majority into one of your decisions. Well, we'll talk about that in just a moment. So if we think about building a tree, there's essentially two questions that we need to ask, okay? So one is, what variable do I split on? And the second question is, what threshold do I use? And both of these questions are answered essentially by the sort of greedy algorithm that we use to build the tree. So, what the tree does is it looks across all of my possible variables and it starts splitting them in every possible configuration, right? And so in this particular case, there's two variables. There's income and there's whether or not you own a home. So let's say in the data, I have so income and home, and you know your income looks like this. And then home is like ones and zeros. Something like this, right? So it will do it'll split it, so possible splits. Less than or equal to 60, less than or equal to 75, less than or equal to 80, less than or equal to 90, less than or equal to 100, less than or equal to 105. And then on the other side, possible splits is just greater than or equal to 0, right? So it's going to look at every possible split, and it will decide which variable and where to split it based on a particular criteria, which is for regression. They call it regression, but really this just means for continuous variables. It's going to be based off of our residual sum of squares. And for classification, or discrete outcomes, this will be based off of a Gini index or an entropy score. And these are as follows. So G is equal to the sum of the fitted probability times 1 minus the fitted probability. Entropy is equal to the negative quantity of something pretty similar. Except you're doing the log of the fitted probability. So I'll note that, for the continuous, you do the residual sum of squares. For classification, you could do the error rate, but actually the error rate is a little bit less sensitive to changes in your splits and your variable decisions. And so I don't actually know the math behind that. They prefer to use the Gini index and the entropy values rather than the error rates for our decisions for choosing these splits. Okay? Yeah?
Is this Gini index related to the Gini index used in economics, measured inequality?
I guess in some ways it probably is. I don't actually know. I mean, also entropy, is that related to the physics entropy? It may very well be derived in some ways, an idea from that, but yeah, I'm not sure. Okay, so the answer to our kind of two questions, right, are I'm just going to look at all possible outcomes and then choose the one that gives me the best value for here if I'm continuous, or the best value for here if I'm classification. This is kind of like stepwise regression in some way, right? You are, instead of choosing specific variables, you're looking at a variable and deciding where to split it, and then you look at these particular metrics instead of our R squared that we were discussing before in a stepwise. And it sort of just brute forces through all of these possible splits, and then chooses the best one, and then it will repeat and continue on. So there is a similar analogy to the drawback in, I don't know what's going on here. All right, there's a similar analogy in the drawback to stepwise regression, which is, so for the order of variables selected, so all splits are considered, and the algorithm will just pick the best at each step. It doesn't consider whether a worse split now will give better splits later, right? And that has to do with computational complexity. So this is, right, akin to, in a stepwise regression, let's say if I'm doing forward stepwise and I omit x2, and later it turns out there's a particular combination of x2 with a different variable in subsequent steps that would have been better than anything I could have gotten. Same here, right? So maybe a suboptimal split now could give a better result with a combination of a split down the line. This doesn't consider that, right? It's a greedy algorithm. It just takes the best split at every consecutive step. Okay? So, when to stop? Right? So, technically, you could do this and continue splitting the data again and again and again until you have one leaf for literally every possible observation, right? But that's probably no good. We're getting overfitting issues. So, the way that decision trees deal with this issue is by doing something called pruning, okay? So you're basically disallowing many leaves to happen. There is a pre-pruning process and then a post-pruning process. So pre-pruning indicating metrics that tell me when to stop before I run the model. And then post-pruning is like you build a really big tree and then you prune back some of the terminal nodes. So what are some pre-pruning rules? So this might include, so you have to have a minimum number of observations per node. You have to have a max depth. So I can only divide my data down some number of layers, right? So this example here would have a depth of 2, right? We split one variable, then we split another variable. Maybe you might have like a max depth of like 30 or something, depending on the size of your data. And then probably the most important one is minimum impurity decision to justify a split. And the idea is, okay, I have my data, I split it up, and I improve the outcome a little bit. But if that little bit is under a threshold, then you're saying, okay, don't bother splitting it anymore. Okay, so all of these things can help to make sure that you don't overfit and that you aren't splitting your data down to the individual observation. Post-pruning is where we build a large tree, then prune it back. And we've seen, I think, principally several examples of this in class, right? So our regularization examples, so lasso, ridge, elastic net, those are the ones where we let it include all the variables in the model, and then we start like regularizing it or trimming the effect of variables based on some tuning parameter. We also saw this in the spline, right? In the what was it called? The last spline that we did, the smoothing spline, right? You let it have as many knots as you want, and then you have a penalty parameter to increase the smoothness. This is like the same idea here. We do something like this. So this is our residual sum of squared, and now we add a penalty term. So this is our number of leaves, and this is our tuning parameter. So as we add more and more leaves into your model, you're going to get more and more accurate, but we risk overfitting. So we add this tuning parameter, and this is like, okay, here's the total number of leaves that you have. As my tuning parameter gets larger, the improvements that you get on your residual sum of squares is getting outweighed by this penalty term in the back, right? If the tuning parameter is really large. If it's really small, you're allowing there to be more leaves to happen. And so how do we choose the tuning parameter size? Cross-validation, right? Same story as with a lot of these other models. Okay, so it's a nice model because it is interpretable, and we'll see what that means in a second. Handles mixed data very well. You don't need to do any scaling. There's no distributional assumptions, which is quite handy. And the big weakness is high variance. So what does that mean? That means small changes can lead to very different trees. And then there's the whole greedy splits are not greedy splits are not globally optimal. That's the whole greedy splits are not optimal. That's the whole thing where a worse split now that may lead to a better split in combination with something else is better later. This can't do that. It just chooses the best split at every opportunity. And then this is bad with smooth/linear relationships. So imagine the relationship between your x and y is like totally linear. It's going to have a hard time deciding where to do the split if the true relationship is linear, right? Because it doesn't matter where you cut. That relationship doesn't change. So this tends to be not as robust with relationships that are very smooth or very linear between my x and my y. Okay? Questions about this? All right. So let's take a look at implementing this in R. So we are going to do decision trees. All right, we're going to load in a couple of other libraries, ISLR2, which has a couple of other data sets, nice data sets that we can use as examples. We are going to use rpart, which is a library that does decision trees and random forests and that sort of thing. There's a separate library called rpart.plot, which helps plot the decision trees. That'll be really handy for us to visualize things, and then I'm going to use dplyr to do some of the data manipulation. Okay, so we are going to use a data set from ISLR2 called car seats. Okay. So let's take a look at what this data set looks like. Actually, you know what? I'll do it over here. So, these are children's car seats, and they look at, for a particular car seat, how many sales it has given its competitor's price, the average income of people buying the car seat, the amount of advertising, how much the car seat actually cost. They have a classification for its shelf location, whether it was in a good, bad, or medium spot. I think that's like the height of the product on the shelf. If it's at like eye level, below eye level, or like too high to reach. The age, education of the people buying, and so on. So we have a bunch of different variables that may help to explain how much is being sold. Okay. So we are going to do, so sales is continuous. We'll do a classification example on a binarized version of the data. Then we'll do a regression example on sales. Okay, so first one, example 1 is going to be our classification tree example. A little bit artificial, but what we're going to do is create a binary outcome. So high is sales above 8. So this is in thousands. Okay. So car seats. So I'm going to perform an operation where I'm creating a variable called high, where sales is greater than 8. Okay, and then what I'm going to do is to create a training/testing data split. So we'll set seed at 2 so everyone gets the same values. I'm going to have a training index. Oh, wait a minute. I did something wrong, huh? Car seats, mutate high, if else. 1, 2, 3.
Double quotes versus single quotes.
Ah, jeez. I would not have caught that in like a million years. Okay. So. Oh my God, please end this. Okay. Let's try this again. There we go. All right, so training index, sample 1 to n row, car seats. I'm going to do 200. And so this will just split it based on what we separated out as training versus testing. So this will be minus train index. Okay. Great. So now we have everything set up. We've divided our sales data and categorized it into high versus low. and then we have our data split into training data and testing data. And so now we want to fit the classification tree. We do want to drop the variable sales because high is derived from it. So we'll do tree class, and we're going to use the function called rPart. So here we do high regressed on everything, which is the dot, as we know, and then I'm going to do minus sales to make sure that's not included in this classification. We're going to use our training data, and we're using method class to indicate that this is a classification example as opposed to a regression example where the outcome is continuous. So I was mentioning the pre-pruning rules just to give everyone a sense of what that is. So the default, these are, so min split, I believe, is 20, so minimum observations per node. For the root, for the intermediate nodes, min bucket is 7, so this is terminal nodes need 7 observations, I believe. Max depth is equal to 30, and then probably the most important one is CP. This is the impurity metric, so 0.01. A split must improve overall fit by at least CP. Okay, so run this. Okay, so there's a couple of different ways we can look at this. So let me do print tree class. And here it will break down the tree for you, where the star is a terminal node. This is kind of the default for rPart. You can do summary tree class 2, and this will give more detailed information for every node. So this particular node has some number of observations. It gives you the probabilities in all the splits. I think these are less intuitive ways of viewing the results. Let's look at a visualization using rPart.plot. Okay, so we put in, our tree class. These are some of these settings that I'm putting in are for visualization settings. So type equals 2 splits the labels below the node. I'm going to do extra equals 104. This shows the class probabilities and the percentage of your total observations in a particular node. And then box palette, this is just for colors. Red, yellow, green. And then we can have a title, classification tree, high sales versus not. Okay, so if I plot this guy, the text is too small. Okay, well, so this is this is the decision tree that we just ran. Hold on. I want to increase the text size, but I don't know how to do that. Let me see. If there's a quick way to do that. CEX maybe. Yeah, here we go. CEX equals 3. Let's try this. Okay. That's too big. Let's try 2. That's better. Oops. Hold on, we're almost there. Sorry. 0.8. Okay, close enough. Okay, so here we should be able to read this a little bit better. You can see the first split is based on price. It decided that the threshold should be at 97. And so are you bigger than 97 or are you less than 97, yes or no? And then it splits the data. So this is the thing. So this first variable and the split location is the thing that gives us the best Gini coefficient or entropy value. Okay. The text at the node, so inside each of these you see a yes or no, and then you see a number below that, and then you should see a fraction or a percentage. So the no is the higher outcome, and then the outcomes are split 59%, 41% in our first one, and 100% of the data is being split here. Okay. So 80% of the data ends up going split out here, which you can see down here. So every node tells us the percentage of the total data that is represented by a particular split. So if I were to add the terminal node percentages, these leaves, this would all add up to 100% at the end. Okay? And then these are the breakdowns of the particular outcome broken down into the two outcomes, so 0.68 and 0.33. So in this particular node, 68% are saying said no to buying. Okay, and you can see the splits continue on to the variables. One thing you'll notice is that price here greater than or equal to 97. Over here we have another one, price is greater than or equal to 125. So when I say, oh, it looks at all the possible splits across all the variables, that includes variables you've already looked at, right? So it did a split on price. So everyone on the left-hand side of this tree is in price above 97. And then later on, it'll do another split at price above 125. So now you have a group of people who are, or a group of car seats that are above 125, and then a group of car seats that are between 97 and 125. Okay. And it's going to break out these variables, these splits, until we meet our pre-pruning conditions. And here, what you'll see is that the purity of these is generally pretty high, right? You are essentially saying this 90% of the time, if I had a car seat that was more than $97, that was in a bad or medium location on the shelf, that was also greater than 125, I will say that it's not being bought with 91%, 91% of the time would be what my prediction would be telling you. Okay? Any questions? So, if you guys recall, we separated the data into testing and training. So if I were to do a prediction on my test set, how well would we do? Okay, so all I'm doing is I'm doing a prediction using my test data, doing a classification type. I break that out into a table, and then I'm going to do the mean accuracy rate. Okay, so here's our prediction table. 97 that are no, we said are no. 25 that were no, we predicted as yes, and so on. So if I were to essentially see how well we're predicting, we're getting about 77.5% accuracy. Okay. Now, let's do post-process pruning. So this is cost complexity. Right, so this is the idea that maybe we've overfit the data. Let's prune back a little bit. Let me see. CP. Oh, plot CP. Okay, I don't know how necessarily useful this is, but at every split, this will tell you how much of the purity is improving based on whatever metric that we're interested in. And you can, I believe this works as well, you can plot this at the size. For every split in the tree, you basically look at how the relative error is improving. So what we're going to do is pick the CP that minimizes cross-validated error. So best CP is we're going to look at our CP table and essentially pick the smallest one. And we're going to use a function called prune using the best CP. Okay, and so now we should be able to look at a new plot of our tree that is now pruned, so that we've reduced the number of leaves based off of the cross-validated the selection value for CP. Okay. Okay, make it even smaller. No. Well, it's always covering the category that I want that I want to be able to see. So, okay. Maybe. Okay, so after we've done the pruning, I know it's kind of hard to see, but just under each node you can see the label. So the first one is still price, then shelf location, then price, age, and the competitor's price. Okay, so yeah, so in this particular example, we've pruned away a number of our terminal nodes to essentially help to reduce overfitting based off of the cross-validation procedure to select the best CP value. We can do a comparison against the non-pruned tree. Doing the same accuracy measure as we did for the previous example. And here the value is almost the same, 0.76 instead of 0.775. So actually in this case, our test performance ends up just slightly lower, but that's just, I think, variation that can happen in like just the sampling. In general, your pruned tree should do at least as good as, if not better, at out-of-sample predictions compared to the non-pruned tree, because we are purposely trying to reduce overfitting. So when we do a test on out-of-sample data, yeah, in theory it would do better or be really close. In this case, it's it's about the same. Okay, any questions about this? I'll get rid of these. Definitely don't have time to get through all of this. Okay, so maybe I'll just give, oh, actually, no, we still have one more part to do, right, before we get to the next part. All right, so that'll be perfect. Forgot, we're gonna also do, so this was an example looking at classification. Let's do a regression tree. So where we had done this thing where we split the sales to be high versus low. Let's do a prediction directly on continuous sales. So tree reg r part, we're just going to do sales, regressed on everything, data equals train. And here we're going to use ANOVA for regression as opposed to the classification. I'm going to skip the prints because I don't think that's very useful. We'll just plot it. Okay, so here, when we do price as a continuous, sales as a continuous variable, now the most important, or the root node changes. It says actually it's whether or not it's placed high on the shelf, yes or no. And then the shelf location, bad or medium, then the price. On the left-hand side, price is the next one, then it splits by age and so on and so forth, right? So you get the point. So the resulting tree from the continuous version is slightly different. Here, predictions are the mean of training y in each leaf. So we can do predict of tree reg on the test data, and then we could do something like calculating our mean squared error, right? So mean of our predicted minus the test, the actual test values squared. So we can see what these look like. If you take the square root of the mean squared error, this is known as the root mean squared error. I think we've talked about this before. So this will be on the same scale as your outcome variable, as y, aka as our sales. So on average, we would expect the predictions from this model to be about 1.57 sales off, right? So the sales are in thousands, so our model would be on average have an error of about 1,500, 1,600 sales off of the actual. And we can compare predicted versus actual, see how off they are, right? And so if you plot your predicted values versus the actual values, if it's like on a 45-degree line, that means that they're predicting exactly, and then any variation off of that means that there's some error happening. So XLab is actual sales, Y is predicted sales. And then we can do an AB line 0 to 1, color equals red. Okay, so here we can see what our predictions for actual versus predicted sales are, with kind of the line indicating where they would be the same. Okay. They're generally centered around the line, which I think is, is a good thing. Not too biased one way or the other. You have still variation that's not being explained in this particular model. but in general doesn't look to be too biased. The last thing that I'll mention is the tree itself gives a qualitative understanding of what's kind of important, right? We can look at where the splits are happening. There's formalized ways of looking at this. And so there is an output called variable importance, and we can plot that like so. So based on like how well the splits are doing in improving the model's outputs, in this case it's continuous, so in improving the residual sum of squares, high variable is the most important, followed by price, followed by shelving location, and so on and so forth. Okay? Any questions about this? Yeah, so to kind of reiterate the strengths of this model, right, it is really nice. It's interpretable. It handles mixed data types really nicely. You don't need to do scaling. But one of the big drawbacks is high variance. So if I were to just change the, actually, in fact, let's do this really quick. Let me just change the, where are we? So I had set a seed here. Okay, let me just change this. So I'm just changing the training data and testing data. Okay, if you guys remember, the first split was price, right? And now all I've done is I've changed the training data a little bit, and it is now saying that the first split should be the shelf location and the next split should be age. Okay? And I bet if I were to do this again, if I just set seed here, let me just change this seed to 15. Different one. Yes. So now shelf location, and then the second one was age, and the previous one now it's price. So very high variance. As soon as the data changes a little bit, the tree changes a lot. And that can give you really different interpretations. So the start of next class, we're going to talk about how folks have dealt with this issue. We're going to get into bagging and then random forests as the sort of natural evolution to improve this particular problem with decision trees. Okay? So that's it for today. We'll end here and continue on Thursday.